Now here is the formal definition of what it means to be continuous at a single number called a. So if a function is continuous at x equals a, then the limit as x approaches a from both sides of this function is going to equal f of a. Now notice f of a is in the range of the function. Now this formal definition isn't so useful until you break it down into a checklist. So here is the continuity checklist right there. Now this is done in numerical order. We typically check to see if the range or f of a is defined. And that means a would have to be in the domain. And then 2, we want to see if the limit of the function actually exists as x approaches a from both sides. And 3rd, not only does that limit has to exist, it has to equal that range value called f of a, which is from step 1. So make sure you're doing this continuity checklist in order 1, 2, and 3, and that's how we proceed to describe whether a function is continuous at a single value. Let's look at this in greater detail with an example. Let's state the x values in which f of x is discontinuous on the interval -3 to 5. Notice -3 is here, and we're trying to figure out whether this function is actually continuous. Now, there's some obvious places where it's discontinuous. That's what we're really looking at. F of x is discontinuous at x equals -1. Now we have to give a reason why. Notice f of -1 is defined. F of -1 is right there. All right, so it satisfies step 1 in our checklist. However, does the limit exist at x equals -1? And I do not believe so. In fact, it's not. As x approaches -1 from both sides, the corresponding function values do not approach each other. Some of them approach 3, and then some of them approach 2. So the reason for this function not being continuous is because the limit of the function as x approaches -1 from both sides does not exist. So it doesn't satisfy step 2 of our continuity checklist. Or I should say, it doesn't satisfy the second item of our continuity checklist. F of x is also discontinuous at x equals 1. And once again, it's because, this one's a little bit more complicated. This time the limit does exist. As x approaches 1 from both sides, we can see that the function values, the corresponding function values, do approach 4. However, 4 is not what we're looking for. We're hoping that it approaches f of 1. But what is f of 1? F of 1 is actually 5. So this time, the reason is because the limit as x approaches 1 from both sides of f of x does not equal f of 1. That is, 4 does not equal 5. So that is another reason why a function is discontinuous. Let's look at a different x value. There's another x value. F of x is discontinuous at x equals 3. And what is the reason this time? This is because f of 3 is not defined. In other words, f of 3 does not exist, or f of 3 is simply nonsense. And so make sure you're going through the continuity checklist in order, and that will give you the most efficient way to describe when a function is discontinuous. Now, can we state the intervals of continuity? The answer is yes. You do have to be a little bit careful. I'm going to try to state the intervals of continuity here. So when is the function connected? Negative infinity up to what? Up to -1. Also, -1 up to +1. What's another interval? 1 to 3. Pay close attention of when you're using parentheses and when you're using bracket. That's very important. Then one more here, 3 to infinity. You want to note that f is continuous from the left at x equals -1. That is, if you look at the limit, as x approaches -1 from the left of this function, it does in fact equal f of -1. Take a closer look. As x approaches -1 from the left, the corresponding function values do approach f of -1. So it is continuous from the right-hand side as x approaches -1 from the right-hand side. So there's some careful analysis using continuity for that specific example. Here are the formal definitions of continuity from one side. Feel free to rewrite this yourself and then learn how to say these vocabulary words out loud. So if you write these symbols, then you learn how to say these vocabulary words out loud. Now, definitions are also if and only if statements. That means you could also rewrite the statements into another sentence, and this counts as a definition as well. So, only for definitions. So pay close attention to your calculus text. If you see a definition, definitions are unlike theorems. All definitions actually are if and only if statements. But, make sure you are reading a definition.